Hey there, we're back, and we want to take a look now at the homework problems in never understood why sometimes it's full screen and sometimes it's not. It's very odd to me. There'll be a trick to this. Okay. Well, I don't know. Maybe we'll figure it out. Maybe we'll figure it out while we're doing this. I don't think it has anything to do with that. I don't know. We'll see. Well, anyway, we want to work with equivalence relations here, and these are relations that are reflexive, symmetric, and transitive, and they have special properties in the way that they partition the set that they're on. Okay? So, in problem 4, we said, okay, define a relation, double squiggle, on r cross r minus 0. So that's r squared, except that we don't have, for the second coordinate, we don't have the x-axis when y is 0, right? We define this relation double squiggle as x is related to x, double squiggle, I'm sorry, xy, let me say it right, xy is related to zw if the first coordinates times the second, now let me get it right again, this first coordinate times this second coordinate equals this second coordinate times that first coordinate. Okay? So we want to show that this is an equivalence relation. I'll do this. It's got this autofocus thing on it. That sometimes works, sometimes doesn't. I don't know. Or it takes up the whole piece of paper. I don't know. I'll keep fooling with it. Maybe that's what I do. I don't know. Alright, so anyway, let's show that this is an equivalence relation. Alright, so we'll start our proof. There, it did it. See how it went to the whole paper and now it's irritating. Okay, I'll figure out how to just do that automatically some way, someday. Alright, let's note that for all xy in r cross r minus 0, that xy would be double squiggle with xy. Since x times y is equal to x, let me see, oh, no, these parts come first, right? This times that equals this times that, right? So this times that equals yx. Okay? Thus, double squiggle is reflexive. Okay? Now, suppose there exist xy and zw that in this set r cross r minus 0 such that xy is double squiggle with zw. Okay? So what does that mean? Well, then it means that xw is equal to yz. X outer, y inner. Okay? Well, then that also means that zy is equal to wx. Right? I did two things there. I relied on the reflexive nature of equals and also commutative property of multiplication. I just wrote it backwards. Okay? Then z, and then let's write this. Zy equals wx. Oh, that's what we had to show, right? Is that I could reverse the order and that you had the relation in the other way. Thus, double squiggle is symmetric. Okay? Now, suppose there exists xy, zw. I need one other thing. How about AB? In R cross R minus 0, such that, okay, x and y, double squiggle with zw, and zw, double squiggles with AB. Now, this is the one that we're trying to show transitivity. This is the one where we have to say, okay, then I can take the shortcut between the x and y and the AB. All right. So let's determine what all this means. Then I've got xw equals yz, and I've got zb equals wa. Alright, so this is a good place probably to kind of step in and say, now what do I need to get? You know, I want to have xy related to AB, so let's think about this just a moment over here, scratch work wise. Really I would want to have x and then b equal to y and a. Okay, so we need to think about how we get that. I could, I guess, maybe solve for, there's a couple approaches here, right? I could solve for w and substitute in here, or I could solve for z and substitute in there. I think that's the approach I will take. Then z equals, and remember b is not 0, so I can say that z is wa over b, and then xw would equal y, and now wa over b. And so I can get that b over here now, multiply those sides by b, it's not 0, right? So xwb equals ywa, and remember that w is not 0. we have, I can get rid of it on both sides, right? So xb equals ya. Then, I shouldn't say thus yet. X B, Y, and A. Thus, double squiggle is transitive. Therefore, double squiggle is an equivalence relation. Okay? So we were able to pull that off. The rest of 4 talks about what does it all mean. Well, for example, give a geometric description of the partition of R cross R minus 0 formed by the double squiggle equivalence classes. Well, the other way to think about this, if you're looking at xw equals yz, and the y and the w are non-zero, right, then we could also write this as xy equals zw, right? Which means that these are things that have equivalent ratios, right? So equivalent ratios would mean equivalent fractions, real number fractions, right? Or things on the same slope line, okay? It's just you have to remember that you're working inside of a space. We don't have the x-axis, okay? We don't have the origin either, so yeah, I know I've kind of left it out, but I just want to make this point that everything then on a particular slope would be in an equivalence class, right? And then you'd have things like this on another equivalence class. And you could use that then to partition the entire set. By altering this very, very slightly, you could get every point in our set. Okay, that's what those equivalence classes look like. Where have you encountered this relation in the context of elementary arithmetic? Well, ratios. All right, ratios are equivalent fractions that you've dealt with before. To an extent, you've kind of dealt with it as slope of a line too. Okay, but our x and our y are kind of reversed here. Could you use the same rule to define an equivalence relation squiggle on R2? Actually, no. And I'll tell you why we need that. If you go back and look at our proof, the fact that we could divide by B and the fact that we could divide by W were crucial in that proof, right? Without that, everything is going to be related to the origin, right? Not equivalence relation. You could go through and show reflexive and symmetric. I think that's fine. But the one that tears up is, let me show you, here's a counter example. One, 2 would be squiggle with 0, 0. Since 1 and times 0 is equal to 2 times 0, right? And then 0, 0 would be squiggle with 1, 3. Since 0 times the 1 is equal to, the 3. 0 times the 3 would be equal to 0 times the 1. Right, they're both 0. But I would not have 1, 2 squiggle with 1, 3, different ratios, right? Since 1 times 3 is not equal to 2 times 1. Right? So having that everything there related to 0, 0 just tears up transitivity on that. Okay, so that's not going to be an equivalence relation if we do that. Okay? Alright. 5 says to find the relation identically, it looks like congruent. Yeah, I'll just say that. Congruent mod 2 pi. Now, we typically think of congruence mod a natural number. So we're going to define a relation congruence mod 2 pi on R by x is congruent to y mod 2 pi if and only if the difference, x minus y, is an integer multiple of 2 pi. So in many ways we're defining it exactly the same way. We're just, instead of saying divisible by 2 pi, we're just saying, okay, the difference is a multiple of 2 pi. And so the question is not to go ahead and prove that it's an equivalence relation. It is. But the question is simply, where have you encountered this equivalence relation and what is its significance? Well, we had a bunch of trig functions, right, that were, if you look at the angles that went into these trig functions, they were equivalent mod 2 pi on R, right? Another way of doing this would be to say that equivalent mod 2 pi on R, define it by x is congruent to y mod 2 pi if and only if the sine of x equal the sine of y, right? That would also take care of this because sine of x and sine of y are 2 pi periodic, or I'm sorry, the sine function is 2 pi periodic. Alright, so if this happens, I know that x and y differ by some integer multiple of 2 pi, right? Or I could have used cosine as well, right? So that's where we've encountered this, is trigonometry. Okay, so not a lot of work on that one. And then 6 says, okay, define a relation squiggle on N by A squiggle B if and only if AB is a square. Okay, so we need to show 3 things: reflexive, symmetric, and transitive. And transitive is the only one here that's really, I think, a challenge. Let's showing A is related to A is really not much. Note that A is related to A for all A in N, since A times A is A squared, right? So the squiggle is reflexive. Okay. All right. Now, suppose there exists A and B natural numbers such that A is related to B. It's A squiggles B. And then we need to show that B will also squiggle A, right? Then AB is A square. But then BA is too. Thus, B is related to A, and squiggle is symmetric. Okay? Sorry, I meant to stagger this over just a little to give it a little structure. So we got 2 of the 3. Now let's get the hard one. Suppose there exists A, B, and C natural numbers such that A squiggles B and is squiggled to B and B is squiggled to C. And we need to show that A will squiggle up to C and bypass the B, right? Then what does this mean? Then AB is a square and BC is a square. Thus, both. Now, I want to think of this in terms of not, which square, but the property that if it is a square, that means that the primes have to occur in whatever primes occur in AB and BC. There have to be an even number of each prime. Okay, that's the only way you can take a square and not have a irrational square root pop up. Right. So thus both AB and BC have prime factorizations where primes occur an even number of times. Okay. And so B is the real common thread here, right? If a prime, sorry, I can't spell occurs an odd number of times in B, then it must occur an odd plus an odd is an even, right? And an odd plus an even is still odd. So it must occur an odd number of times in A, and then also in C. Giving an even number of the prime in AC. Similarly, if a prime occurs an even number of times in B, then I can't odd it up with A or with C. An even number of times in both A and C, and so in AC. Thus, AC, having an even number of each prime that appears in its factorization, is a square. So, thus, A is squiggle to C, and squiggle is transitive. Therefore, squiggle is an equivalence relation. Okay. And I'll just kind of, sorry, that took more space than I thought it would take to write, but there we go. Okay. So, kind of with that in mind, it asks us, okay, describe the equivalence classes that go along with 3. Well, 3 occurs, it's a prime itself, it occurs one time. So everything related to it's going to have another prime factor of 3 in there. So the equivalence class with 3 would be the set of all things of the form 3. You're going to have another 3, and then everything else can be squared. You know, everything else has to occur then at even prime iterations, right? All in the natural numbers. Okay. 9, on the other hand, has 2 factors of 3. So anything, all the squares, you know, we don't need to add anything to that. Just all the squares would be, any square times that's going to be a perfect square, right? And then with 99, okay, now I should be writing this off to the side. 3 is its own prime factorization. 9 is 3 times 3. And 99 is 3 times 3 times 11. Well, we've got an even number of 3's there, but we've got an odd number of 11. So things here would have to have another factor of 11. So when you multiply them, you got 11 squared. And then after that, you can have all the, oops, I didn't mean to put square there, in the natural numbers. Okay? So to kind of sum it all up, it says if A is squiggle to B, which attributes of A and B are equal? Well, the presence of prime factors that appear an odd number of times. In the prime factorizations. Okay? Alright, that gets us through the homework problems in 5.2. And we will pick up, I think we worked a few more out of 6.1, so we will take up there in just a few minutes. Hope this is helping, and I will see you soon.